All right, let's move on to aluminum now. All right, and for aluminum, aluminum is right below boron. It's the first element in the third row. So what we're going to do is draw our 1s orbital. Aluminum is already drawn there. Aluminum has a full 1s orbital. Then 2s. Everything in the second row is going to be filled. Since aluminum's in the third row, everything below that has to be filled. So there's an electron up and an electron down. Now we have to fill the 2p orbital, and it's going to be completely filled because we got to get all the way down to the third row. But I'd like you to practice doing it in the proper order. So you do an up arrow, and then you don't put the down arrow in right away. You put in an up arrow in the next subshell and an up arrow in the next subshell. And that's called Hund's rule. And Hund's rule says you have similar electrons of similar spins, in this case up arrows in other words, and you spread them out through all the subshells until you put one electron in each subshell. Now we need to come back and we need to put a down arrow. And the down arrow represents an opposite spin from the up arrow. Electrons are negatively charged, so they repel each other. But what opposite spins does is it magnetically kind of attracts them to each other, so they're not totally attracted to each other, but they don't repel each other quite as much as they would if they had the same spin. You don't need to understand anything more about it than that. That concept of spin is simply opposite spin electrons have to be paired up in the same subshell. So that's called the Pauli exclusion principle. So let's review that. Aufbau principle says you stack things up from lowest energy to highest. Hund's rule says you take similar electrons with the same spin and you spread them out among the subshells before you start pairing them up. And then the Pauli exclusion principle says when you do start pairing them up, they have to have an opposite spin if they're in the same subshell. So we're going to put another one here and another one here. And now we have filled up the 2p orbital. An important point to understand is whenever you have a full p orbital, that's a noble gas. The only exception is the 1s orbital is helium. So we're going to put that in a block here. At the end of the 2p orbital, you have neon. So anytime you get to the end of a p orbital, it's not true of a d orbital or an f orbital. It's only true of p orbital. That represents a noble gas. All right, now we're off to the 3s orbital because we have to get down here to 3p to aluminum. So 3s is sodium and magnesium. So we're going to have at a slightly higher energy level than the 2p's is a 3s there. And now aluminum is the first element in the p subshell over here. There's 6 elements there, and aluminum's the first, so it gets 1 electron there, and we're all done with that. So that's the electron configuration for aluminum. Now we write it out in its notation. So it's just as simple as reading these. So you have a 1s, and you have 2 electrons in that. Then you jump up to the 2s, and you have 2 electrons in that. Then you come up to the 2p, and you have 6 electrons there. As I said before, you don't break this into px, py, pz. It's just the p suborbital. Okay, so it's 2p6. There's 6 electrons. Now we're up to 3s, 2 electrons there, and then finally 3p, and there's 1 electron there. You can see that's starting to get a little bit long there when you write it out this way. In the condensed configuration, there's aluminum. So we go to the noble gas in the row that's before, that's neon. And so we just put Ne in a block. And then we continue on where we started. So where is neon? It's at the end of this this full P subshell right here. So that's neon right there. So now we just write all of that as neon, and then we can just continue on with the rest of it. So it's 3s2 and 3p1. Okay?